in the transition are very complicated and interdependent. Of nearly two-dimensional waves, the Thomaine-Schlichting waves, followed by the appearance and growth of three-dimensional disturbances associated with streamwise vorticity. Then turbulent spots can be seen. And finally, fully turbulent flow appears. Here, the exact position where growth of two-dimensional disturbances begins depends on random small-scale fluctuations in the flow, and therefore varies with time in a random way. This boundary layer around a channel bend is made turbulent by placing an obstruction in the layer upstream. The obstruction stimulates the naturally occurring processes and hastens the onset of transition. The flow here is all downstream. Removing the trip rod results in separation and backflow. Bubbles accumulate at the separation point. In this diffuser, which was used before, we have made the bottom boundary layer turbulent by inserting a trip rod upstream. The turbulent boundary layer is able to withstand the adverse pressure gradient in the diffuser, while the laminar layer along the top wall is separated, allowing reverse flow. Timelines show that in the turbulent boundary layer, there is no separation. The overall flow is downstream. To see why a turbulent boundary layer can withstand a larger unfavorable pressure gradient without separating, we shall again examine the flow along a flat plate. The boundary layer on the bottom side is laminar and two-dimensional. On the top side, the boundary layer has been tripped by a wire placed well upstream. Unsteady motions in the turbulent boundary layer are three-dimensional. Some of the motions are perpendicular to the plane of view. These timelines correspond closely to the instantaneous velocity profiles for the two types of boundary layers. Superimposing a number of displacement lines enables us to obtain a mean velocity profile for the turbulent layer and the laminar layer, and at the same time gives an experimental notion as to where the fluctuations occur and how large they are in the plane of mean motion. In this photograph, we can compare mean laminar and turbulent profiles. Here is the laminar one, the turbulent one. And here they are superimposed. The velocity gradient normal to the plate is larger for the turbulent layer, and it therefore has the larger wall shear stress or drag. The circulation is the same for both layers. Both boundary layers therefore contain the same amount of vorticity per unit length of the plate. However, the distribution of vorticity in the two layers is very different. There is more vorticity near the plate in the turbulent layer. The distribution of momentum in the two layers is also different. turbulent layer, high momentum fluid is moved toward the plate, and low momentum fluid is moved away from the plate by unsteady, random motions. There are larger shear stresses and more momentum in the turbulent boundary layer than in the laminar layer, and the turbulent boundary layer is slightly thicker. In the diffuser, the turbulent boundary layer along the bottom wall does not separate, while the laminar one does, because the three-dimensional interchange between regions of high and low momentum fluid in the turbulent layer is more effective than the molecular diffusion in the laminar layer. Similarly, a turbulent boundary layer on the upper surface of this airfoil prevents large-scale separation, or stall, until a very high angle of attack. The blades along this wing are called vortex generators. They introduce axial vorticity, which enhances the naturally occurring rotary momentum interchange in the already turbulent boundary layer. Such mixing delays or prevents separation. In this film, we looked at flow along a flat plate and then saw the effect of pressure gradients on boundary layer flow. Now we can understand how this cylinder influences the flow on this plate. Without the plate attached, there is a static pressure increase along the stagnation streamline with a corresponding decrease in velocity. When the plate is attached, a positive pressure gradient is imposed along the plate in the flow direction. This unfavorable pressure gradient causes boundary layer separation, and the flow field is radically altered.